Hey everyone, so in this video we're going to be talking about sampling proportions. So just a quick review of sampling distributions, which we talked about last time. If the random variable x has a mean of mu and a variance of sigma squared, then the random variable x bar, the sample mean, has a mean of mu, which is the same as the mean of x, and then a variance of sigma squared over n, or the variance of x over n. And then we talked about how if x is normal, then x bar is going to be exactly normal no matter what the sample size is. And if the distribution of x is unknown, and we have a sample size greater than or equal to 30, then the sampling distribution of x bar is going to be approximately normal. And the central limit theorem is what told us that. And if the distribution of x is unknown and the sample size is less than 30, then we don't have enough information to determine the distribution of x bar. So now let's talk about proportions. So a proportion is the frequency of one outcome relative to the number of observations. And for samples, we call this p hat. And p hat is going to be calculated by taking x and dividing it by n. And x in this case is going to be the total number of successes. And the reason I have successes in quotes here is because it doesn't necessarily have to be a success, it's just whatever event we're interested in. And then n is going to be our typical n, where it's the total number of observations or our sample size. So a proportion is always going to be between 0 and 1. And then just like with means, proportions can be a population proportion or a sample proportion. And one thing to note here is that even though usually we use Greek letters for population parameters, we're actually using an English p here. And with the sample proportion, we're just putting a hat on it and calling it p hat. Now let's look at an example. So suppose we're interested in knowing the proportion of Democrats in the United States, and we randomly ask 50 people what party they identify with. And after we ask those 50 people, we find that 17 of those 50 identified as Democrat. So our sample proportion in this case, or p hat, is going to be 17 over 50. We had 17 people identify as Democrat, and we talked to 50 people total, so our sample proportion is going to be 0.34. Now our population proportion, which is P, is going to be the proportion of all people in the United States who identify as Democrat. And that's the population parameter that we're interested in, and that's what we're trying to estimate using the sample proportion. So remember, just like the sample mean, the sample proportion is going to be a statistic. And remember, we talked about how statistics are random, and the sample proportion is going to have its own distribution. So the mean of the sample proportion is just going to be p, the population proportion. And the variance of the sample proportion is going to be p times 1 minus p over n. And then the standard deviation of the sample proportion is going to be the square root of that. Now, the central limit theorem applies to proportions too, and the conditions that we have to check are just a little bit different. So the sample needs to be independent, just like with the central limit theorem when applied to the sample mean. And then n times p needs to be greater than or equal to 5. Or in some cases, you'll find that this condition is n times p is greater than or equal to 10. But for this sake, we're going to use 5. And then n times 1 minus p needs to also be greater than or equal to 5. Now, the only problem with this is that most of the time we don't know what the population proportion actually is. So in that case, we'll just have to substitute this p with p hat. to check our conditions. And if those conditions are all met, then the sampling distribution of p hat will be normal. So going back to the first example, let's say our population proportion for Democrats is actually 0.29. So if we ask 50 people, what are the mean and the standard deviation going to be of p hat, the sample proportion? Now remember, the mean of the sample proportion is just going to be the population proportion. So the mean of the sample proportion is going to be 0.29. And then the standard deviation of the sample proportion is going to be the square root of p times 1 minus p over n. So when we plug that in, we'll have 0.29 times 1 minus 0.29 over 50. And that'll give us 0.0642. And then to check our conditions, we declared earlier that we were talking to people randomly, so this sample is going to be independent. And then for the second condition, n was 50 and p was 0.29, so n times p is going to be 14.5, which is greater than or equal to 5. And then n times 1 minus p is going to be 50 times 0.71, which is going to be 35.5, which is greater than or equal to 5. So we can say that p hat is going to be normally distributed. So just like with x and x bar, we can standardize p hat. And just like before, to do this, we take p hat, subtract its mean, and divide by its standard deviation. And when we do that, we'll get p hat minus p over the standard deviation of p hat. And that means we can handle the usual problems from before involving the normal distribution. So from the Democrat example, we had a population proportion of 0.29. And let's say we were asked about the probability that a sampling proportion of 100 people is less than 0.3. So we need to determine the mean and the standard deviation of p hat before we can do this calculation. So remember, the mean of the sampling proportion is going to be the population proportion. So we know that right away because that's given to us. That's 0.29. And then the standard deviation of p hat is going to be the square root of p times 1 minus p over n, which is 0.29 times 1 minus 0.29 over 100, and then the square root of all of that, and that'll give us 0.0454. And then checking our usual conditions, we know the sample's independent. We know n times p is 100 times 0.29, which is 29, which is greater than or equal to 5. And then n times 1 minus p is going to be 100 times 0.71, and that's 71, and that is also greater than or equal to 5. So now, since all three of the conditions are met, the central limit theorem tells us that p hat is going to be normal, and we can carry on with the typical calculations. So we determined that the mean of the sample proportion is going to be 0.29, and the standard deviation of the sample proportion is going to be 0.0454. And we want to know the probability that the sample proportion is less than 0.3. And since now we know that p hat is going to be approximately normal, we can do our typical calculations from before. So we wanted to know the probability that p hat is less than 0.3, and the first step here is going to be to standardize this. And we standardize by subtracting the mean and dividing by the standard deviation, and we already figured out what both of these were. So we could subtract the mean and then divide by the standard deviation, and then we'll be left with the probability that z is less than 0.22. And This is in terms of z now. Now we could just look this up on the table. And when we look it up on the table, we'll get 0.5871. So the probability that the sample proportion is going to be less than 0.3 is going to be 0.5871. So a lot of similarities between the sample proportion calculations and the sample mean calculations. But anyway, that's all for this video. I hope you found it helpful and enjoyable, and I will see you in the next video. Take care.